Luckily, it's that easy. Okay. Like I said, start, stop. We expect it counts to 0 to 9 and then back to 0. Yeah, the reset button, when that's pressed, it always goes back to 0 regardless of what state you're in, regardless of what's happening. This is an asynchronous reset. It means that no matter what the clock is doing or anything else, the timer goes back to 0. Okay? Then we have some details about tracking time. It says that we have a 50 megahertz clock, a very stable 50 megahertz clock on our board, and we want to generate from that a 1 hertz signal so that we can tick the clock every 1 second, and we will discuss that. Okay, and then you get your deadlines and other stuff. I highly recommend you read through the entire lab to understand exactly what you're doing. This actually tells you through what you should have completed by week 1 and by week 2 and by week 3, etc. Okay, so let us begin by coming over to here and making a new chart. And I'm going to talk about state machines. Now, you talked a little bit about state machines in your lecture yesterday, as I understand. So, in order to design more complex systems, we start to break up the logic that needs to happen into different states. So typically we have states and we have data, and that data changes depending on what state we're in. So let's go ahead and make a note here about states. So based on our quick glance of the document, what states would we have? Running, paused or stopped, reset. We have a reset state, and then I always like to add an initial state. This is just the way I design things. I like to have a known starting state that doesn't occur anywhere else, because it probably isn't necessary for this design, but it makes more complex designs easier. So I'm going to make an initial state here. When you go to actually design yours, you can choose whether or not you want to include it. It might actually make things a little simpler if you don't in this case, but I'm going to do it in my design anyways. Okay, so we have an initial state here. I keep trying to find the best way to lay this out. I'm going to try sideways now. I don't want, it gets really confusing when we start having crossing wires. So we have initial state, we have our running state, we said. We have our stopped state, and we have our reset state right there. Okay, so those are our states. Let's make another one and ask about what is our data. What data do we need to track? What's that? Yeah, our count. Or so count. What's that?
Current state.
Current state. Okay. Other things? Well, current state, that could be, we also want to know probably whether or not we've start, stopped, or reset. I guess that goes under current state as well. Do you mind if I break that out into start, stop, and reset? Start, stop, reset. I think that's what you meant, right?
Yeah.
Okay. So yeah, that's about our data there. Count, start, stop, and reset. Trying to think if there's anything else there might be, but we'll come back to it if there is. Alright, so then the next thing is we need to make some decisions from every state about what to do, what has happened. So there ends up being about 3 decisions to make for every state. Cool. Zoom in on that a little bit more. Alright, so the decisions, or the questions we want to ask are basically what button was pressed, right? So start, stop, reset. So from initial, if we start, we go, where do we go? Running, yep. Otherwise, we may be stopped. If that's the case, actually, here, I'm going to go around the other side. It's going to make things a little bit cleaner, I think. Running. That should be yes, not no. That's why I need a mouse. So if we stop, then we're going to stop. If we reset, then we're coming over here to reset. So rather than calling these yes, 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 I will say start, stop, reset. All right, there's our first one. Okay, from running, we're gonna have the same thing. We're gonna have start, stop, reset. So from running, if we hit start, what should happen? Yeah, just go back to running, right? Just keep doing your thing. Nothing happens. From stop, we go to stopped. And from reset, should probably go to the reset state. Cool. All right. From stopped, if we go to start, there's no good way. I'm always gonna cross lines. I always get myself in this trap. Oh well. Cool. And if not, then we probably went to see what happens if we go stop And from stopped, if we press stop, it makes perfect sense that we would just go back to stopped. And reset always goes back to reset.
So we have 3 buttons. There's start, stop, and reset button.
Yeah. Your board only has 2 buttons, so one of them will actually be a switch.
Okay.
And which one you make the switch is entirely up to you. Okay. Alright, and then reset is interesting because it doesn't actually worry about buttons. It's concerned with the state that it came from. So if prev state is equal to stopped, or if prev state is equal to running, or if prev state is equal to initial. Boop. 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 And then these would all be no, not yes. No. And no. Okay. And if prev state is equal to initial, basically in every case we just go back to where we came from. Pull it off of that line. So this is reset or from reset. I don't know. Let's say yes. Leave it. I'm like, what do I make that line? I don't know. Let's leave it as it is, I guess. Okay. If prev state is equal to running, then of course we go back to running. Should be a yes. And if prev state was equal to stopped, then we go back to stopped. Alright, well, it's no better or worse than any of the others I've done. Okay, so those are our states. That describes our state transition. I mean, that looks a little awkward, but oh well. You get the general idea. And now we need to describe the data that's in each of these states. So from our initial state, we said the data was count. So what's our count? 0. Great. Our start should be equal to 0. And our stop should be equal to 0. Basically everything in initial just gets zeroed out, right? Or actually stop, does that make sense to be 0 or should it be 1? You can design it either way. It's kind of your call. Alright, we'll make it 1 then. So I'm going to say the same thing that I've said in every class, which is that this is just a design. This isn't necessarily the design. You can design a stopwatch in many ways. This is just one way. the way that made the most sense to me. Okay, count is equal to, I'll say t here. It's just whatever the clock pulse is, right? And we'll put 0 through 9. So we remember that after 9, we have to reset. Make it a little bit bigger on the side here so it doesn't. There we go. Because after 9, then it has to go back to 0. It has to cycle. Okay, start should be equal to 1 because it's running, right? And then stop equals to 0, and reset equals to 0. In the stop state, t is equal to what? It's just t. Yeah, it's just whatever it was, right? So let's say t is equal, or count, I guess we call it. So count is equal to t. So count is equal to t. Just where t is whatever our count was when we and then start is 0, stop is 0, reset, stop is 1, and reset is 0. Cool. Cool. All right, and then finally in our reset state, we have start is equal to 0, stop is equal to 0. Actually, no, these are just whatever they were, right? So start is equal to S wherever it was. Stop is equal to ST, whatever stop was originally. Reset. And this is going to trip people up, but we're going to say that reset is equal to 0 in this state. And the reason I'm going to say that is because we are going to transition reset to 1 based on this decision here. So really, reset is 1 only at the moment that that button is pressed. Then we transition to reset. We want to make sure that we uncheck the reset flag so we don't get stuck in a reset loop.
Would count be 0 there too?
Yes, and count is equal to 0. Cool. Looks good to me. So now we get to design the thing. I will publish this document or one like it so that you can have it to reference. So let's go. Let's think about how we might design this. All right. And get rid of all of this stuff here. I'm gonna leave this here. No. All right. So I created a module. It's a basic, simple module. It says that we get an input, a wire that's start, stop, or reset, which, you know, we have those 3 inputs, and then we have an output state. The point of this FSM module is an abstraction, so it doesn't actually handle the data transitions. It doesn't change the data. That's actually going to happen in your top level module. Its job is to track what state you're in. So we're abstracting as much away as we can so that each module can handle only what it needs to. Your top level module handles the actual data. Your FSM handles the state transitions. If you try to pack them into the same module, you'll end up with a lot of latches because you're handling clock signals and asynchronous stuff all at the same time, and it gets very difficult to juggle, so we abstract it away as much as we can. So it's pretty simple. This is just an always block. Oh, I wanted to point out these parameters. I hadn't explain these yet. This is a new syntax you've never seen before. Parameters, which we will use again in a minute, can be set during the instantiation of a module. They can be referenced from outside that module. So from the top level module, I could actually say like FSM dot initial state to get that value out of the module to know what it is. So it's kind of like static variables in that sense. And they can be changed. Like I said, they can be changed when you instantiate them, and they can be referenced outside and inside the module. So I've got these constants here, not to change them, but because they're going to be very useful to reference outside of my module when I need to know what state I'm in, and because it's going to make my syntax in my FSM a lot simpler. So I'm going to say always at sign, just as I always do, and then we want to wait for start, stop, or reset, right? Pretty simple. And end. Cool. So we got our start, stop, reset signals. Now what do we want to do? Okay, so I'm going to add one more new piece of syntax here. I'm going to say negedge start, negedge stop, negedge reset. And this means that they're only going to trigger on the negative edge or the falling edge of the clock or of the signal. It doesn't have to be a clock. In this case, the reason they're negedge is because on your board, the buttons are active low. So they're normally high buttons. When you press them, they go low. So now we just need to check and see which one is low. Basically, if we didn't have the neg edge, we would have to check if it was high or low, so that we could ignore the high portion. And this way, we know that it's always going to be low, and we can just say if negedge is equal to, not negedge, if start is equal to 1 tick b 0, then we know we're in start. Else, if stop is equal to 1 tick b 0, begin, end. Else, begin, end. I want to make one other thing kind of clear here. I saw a few people having troubles with Lab 3 because they had everything defined as else ifs. So it's if, else if, and there was no final else statement. Even if you have every case covered in all of your else if blocks, the compiler will not infer that for you. So it assumes that because you specified else if, there must be some other else condition that you're not meeting, and it will create a latch. You'll never get to that latch, and it probably won't affect your ultimate design, but it's wasted logic. So always we'll just make sure that we're explicit when using case statements. For example, you have to always have a default case. Same thing. Alright, so if start is 0, that means that we've pressed the start button. So what shall we do? Get the clock. Well, so again, we're only, you're right that we will have to get the clock going, but we're only doing transitions in this module. Yeah, exactly, yeah. So we'll say state is equal to running state. Then else if stop. What should state equal? Stop state. Need my semicolons there.
If stop equals 0, it should be stop state?
Yep, because these buttons are normally high.
Okay.
So that means that when they're not pressed, we're getting a high signal. When they are pressed, we're getting a low signal. Now, one of those is going to have to be a switch. And so depending on how you want that switch to behave, you might take the neg edge off completely, or you might just accept that it has to be the neg edge, and then you have to flip it twice. However you want to do that.
Okay.
That's entirely up to you. And then state is equal to reset. And then up here, we're going to say state is equal to, reset state. Initial state. All right. Yeah, so we're going to go to the reset state as the final alternative, and where I specified in the diagram here that reset was 0, that will be part of your reset logic. All right, so there is our state machine. That's not too bad, right? I want you guys, I'm going to publish the document. I want you guys to take some time and understand it, because knowing how to build state machines is going to be imperative. Like, you're going to have to know how to create these, because the logic is only going to get more complex as we move forward. And I'm not going to, like, for instance, in the next lab, I probably won't create the state machine for you and tell you what it should be. That's going to be part of your exercise. Yeah.
How can we check it to be 0 instead of 1?
Because the button is normally high or active low. In other words, the signal that the hardware receives when the button is not pushed is a high signal. And when you push it, then it's a low signal.
And that's what the neg edge means.
That's what the neg edge means. So it only triggers if we didn't have the neg edge and we just left it start, stop, and reset, this else block would be inaccurate, because
Always think that it's either running or stopped.
right. So because it would trigger if it was low or high. In which case, if it was high, this else block would go, and it would always just keep going back to reset. That's what would happen. You'd push it low. This, for instance, start would trigger. You'd let go. It would go high. It wouldn't match any of these two cases, so it would come down here and reset for you. So without the neg edge, anytime you let go of the button, we would get to reset. All right. So we have got our finite state machine. Now let's talk about how we're going to make our clock work. We want a 1 hertz clock, and we have a 50 megahertz clock. So let me go ahead and pull up my handy dandy little paint here. This is my very nice job here. This is a 50 megahertz clock. This is our fast clock up here. Okay? And this is going to be our slow clock. And what I want to do is I'm going to use pause edge. I want to trigger my whatever logic I use. I want to trigger it only on the rising edge. And the reason I want to trigger it on the rising edge is so that I know that every time I get into my logic, I've gone one full period. That's what this T up here is. It's one period of my 50 megahertz clock. Which means that I have basically 1 over 50 e to the 6, 1 over 50 million counts. So essentially what we need to do for our clock divider, yes, that's fine. Come on, clock divider. All right, take all this out so that you guys don't have all the secrets. Okay, but our clock divider we see here, it takes an input clock and it outputs a slow clock. and that's it. So we need to track the amount of fast ticks that we get so that we know when to tick our slow clock. So this guy is going to have an internal slow clock that it outputs. So it's going to have an output of a slow clock, and it's going to need to be able to trigger that clock high and low at a period of 1 hertz. Or, well, at a period of 1 or 1 hertz. Frequency and, yeah, anyway, you get the idea. So, back to the idea here, we're going to have some kind of internal counter, right? And I'll say reg, and we'll make it a 32-bit reg here so that we can count to very high numbers. And we'll call this count. We'll make it equal to 0. And we don't have to specify that it's a 32-bit number. We don't have to like 32 tick B, because it is a 32-bit number, so we can just put our regular digits, and Quartus will assume it's a 32-bit number, and in this case it's right. Alright, so now back to my notepad here. This kind of gives you the basic structure. If I am going to count, I'm going to increment my counter at every period, every positive edge. Then how many times do I need to trigger or count before I change my slow clock? So if it's high, then it needs to go low, and then it needs to go high. So what's that? It would be 50 million.
25.
It's 25 million. You want to explain why?
Because you want the full period. So halfway through it has to change state before it comes back.
Exactly, yeah. So that's why these little X's are here. Basically saying that we have this edge here, we need to go low. This has to happen at 25 million ticks, so that at 25 million more ticks, we go high, which gives us a full period from here to here of 1 hertz, or of 1, period of 1, which gives us a frequency of 1 hertz. Does that make sense? Are there questions about it? This is your opportunity to ask questions about what we're doing here. Okay. In that case, it's really, really simple. We have our slow clock. We need to give it a default value. Should our slow clock be high or low to start? I don't care. High. Okay. We will make it high then. Slow clock also needs to be a reg, not a wire. That was my bad. Can someone explain for me why it needs to be a reg? So I'm sure that you understand. Oh, why? What's that? Yeah, exactly. I'll be like, exactly. I'll be manually changing it, manually setting it to one thing or another, and so it has to be a reg. So always, we said we were triggering on the positive edge of this clock. So pos edge instead of neg edge. And then CLK gets the clock.
Do we need the at symbol?
Yes, we do. Thank you for reminding me. I actually, I'm going to be honest. I don't know what the at symbol does. I don't know why it's there.
Seems like it might not need to be there.
Begin, end. All right. So then, on the positive edge, what do we need to do?
Increment the count.
Increment the count, okay. So it's a count is equal to count plus 1. Are we done? Is that all we need to do?
We need to check whether it's 25 million or is that...
Yeah, exactly. So that's the other thing we need to do. If count is equal to 25, 1, 2, 3, 4, 5, 6. because it's a 32-bit register, it's going to interpret that decimal number as a 32-bit integer, and in this case, it's right.
So if you're lazy, just make everything every red's a 32-bit one, even if you don't need it.
Yep. Begin we say, so clock is equal to not clock. Right? We're just going to invert the clock. So if it was high, then it's low, then it's high, then it's low. Does anyone see a problem with this design? Oh well, yes, that is a typo. Thank you for catching that. But a more subtle, a more subtle problem here.
I would
Oh.
do greater than 24,99999.
Okay, yeah, that would be one thing as well. You could end up 1 like millisecond off or microsecond off.
Don't
True.
need to check if it's a multiple of 25 million.
So same sort of situation, and these aren't necessarily wrong, but you're going to end up with a latch here. Do you see that? Was the first thing I said at the when we were doing if statements. There's no else statement, exactly.
Oh.
So there's no else statement, we're going to get a latch. So better than putting this at the top would be to put it in an else statement here. Do that. We always need to think about that because it's not like software programming. It will not, it'll create a latch for you. And best case, you're wasting space. At worst case, you're creating a design that won't work. And so I would say as like a design principle, if there's a situation like this where you can give your else block something to do by just like rearranging your code, do it. Make sense?
And then again, if timing was an issue, you want to put that in your if block as well.
If
For a millisecond.
Sorry, can you tell me that again?
The increasing your count
Oh, right.
if a millisecond is.
Then I actually want to say that my count is equal to 0, right? I want to reset it.
So that
Yep.
way we don't have to check if it's a multiple of 25 million.
Right. And once it gets to 25 million, we'll just reset the count and count up to 25 million again. All right. So there's our clock divider. Boom. These things seem complex, but when you actually see their code, and you're like, okay, it's actually not too bad.
Explain pause.
Yeah. So a clock, I'm going to come back over to my fantastic drawing, has 2 edges. It has the edge where it's coming from negative to positive, and the edge where it's going from positive to negative. And so when we put pause edge, we only trigger when the signal goes from negative to positive. And when we put neg edge, we only trigger when the signal goes from positive to negative. All right. Other questions? Cool. All right. Save this. It's our clock divider. All right. Now we get to talk about latches. Latches that we actually want. I'm going to actually delete all of this and we'll start from the beginning. Okay. So what we're going to create here is a D-latch, not a flip-flop. A flip-flop is a little bit more advanced than a latch, and you'll discuss those in lectures later, probably on Thursday. But for our purposes, we need a latch. And before I jump in there and say you need a latch, let's discuss why. So the purpose of a latch is to save a previous state. Every time I told you that the compiler creating a latch is bad, is because the compiler's latch is not synthesizable, and because you don't want to create latches unless you know that you need them. So then the question becomes, in our design, where would we need to save the previous state? Where would that become an important feature in our design?
When we stop it.
When it's exactly. So when it's stopped.
And when it's running.
Can you tell me what you mean by that? Because I think of stop, but I'm not sure about running. So.
Running, it needs to know that it's still running.
Oh, yeah. So the state would need to know that it's still running. I think we could get away without a latch in that case, just based on how we defined our finite state machine. What do you mean you can't find it? It does too exist. It's right here. All right. Just based on how we defined our finite state machine, the reg will hold the memory for us.
Okay.
It is true, what the reg is actually doing is internally creating a flip-flop. So that's actually doing that for us. But particularly, we want one that we can control ourselves. We want one where we can tell it to hold a value or tell it to release a value via a switch. That's what a latch will allow us to do. But you are right. And for all these regs, internally, those are actually going to create flip-flops. So back to our latch here for a second. So you said when it stopped, what do you think, what do you mean by that? Elaborate.
When it stopped, we need to hold the state goes in just in case it wants to run again.
Yeah, exactly. So we need to hold on to our count so that it doesn't keep incrementing, right? What's the best way to do that? Can you think of? Like, how are you going to assume for a minute we have a latch? I haven't discussed how it is, but we have a latch. We'll be able to pause it. What value are we going to pause?
The current time.
You can pause the current time, but what actually drives the current time? The clock. So if we pause the clock, the time never changes, right? It's going to be a lot easier to pause the clock and just not have the clock ticking, because otherwise you're going to have to, if you try to pause the t value or the count value, whatever we're using, you could do that. There's no reason you couldn't. But I think that the logic is going to be more complex. I encourage you to try it. Either way should work, but I do think that pausing the clock versus holding on to the t value is going to be easier, especially because if the clock is still ticking, but you're holding your t value, then when you release it, you don't know at what state the clock is in. So you might get skips, right? Like, what would happen if we paused t and then we released it when we were halfway between the clock cycle? You'd have a situation where instead of counting a full second, you'd count like a millisecond, and it would change the value. So there, I think we're going to pause the clock so that we know that we're always on 1 second cues. But that's the idea. So now we need to figure out how we can do that. And for that, I'm going to refer to your book. This is on page 255 of your book. Okay, and this is a gated D-latch is what this is called. And this is the circuit if you wanted to define one using just your primitives. We actually won't do that. We will use our always logic, our behavioral logic to do this. But the idea is that when data comes inside D of this device, if the clock signal is high, then the data propagates out of Q. It's transparent. So long as the clock signal is high, then the value on Q is whatever D was. Does that make sense? So when the clock signal goes low, it doesn't matter what D is. Q will always be whatever Q was the last time that the clock was high. So if we look at the timing diagram down here, we can see it better. We have here at this tick here, the clock goes high. Now prior to the clock going high, the data was high. This D latch here, right? Now, as soon as the clock goes high, and for as long, as soon as the clock goes high, the data on Q, well, Q is whatever the data was, right? It's high as well. Does that make sense so far? Now we have a situation where the clock here, it goes low, right here. While the clock is low, data also changes to low. But if we were to draw a line straight down, we would see the value on Q is still high. That's because if the clock is low, D cannot propagate over to Q, so Q retains its original value.
If the clock went low after D went low, then Q would go low, right? And then
Yes.
it would stay low when the clock went low.
Yeah, so if the clock was high and D went low right here, for example, then as soon as D went low, you'd see the propagation over at Q. So you'd have like a little small tick down here.
Like in time,
What's that?
like in time block 3.
Like in time block 3. Exactly. So in time block 3, if we look at that, let's say the clock was low, the data was high, the clock went high and the data is still high. So now we have Q being high, right? Because Q gets the data, so it starts at high. Now, the clock is still high, but the data goes low. Which means that as soon as the data goes low, Q also goes low. Because the clock is still high. Then, the clock goes low, and D does some funky stuff over here, but Q doesn't care because the clock is low. That make sense? This is a gated D latch. It is the fundamental building block of larger memories. When we're actually dealing with RAM, for example, when you put like the RAM inside your computer, that's all this is a whole bunch of these guys sort of cascaded together in a way to make what's called a flip-flop, which we'll discuss more later. But that's what your RAM is. Kind of cool. So let's come back over to here. So according to this design, we need a D, a clock, a Q, and we're not going to worry about Q naught because we're not going to use it anyways. You don't have to include Q naught in a latch if you don't want to. So, input. Now, here's a tricky thing. How big is the input that we're going to pass into our latch? How big is that data? What size is it?
32 bits.
Could be 32 bits, not necessarily. Could be 1 bit, right? Depends on what we're trying to latch onto. So we can specify a variable number or an we can specify this in a way so that we can specify how much data we're going to pass in, so that that's configurable. And so that's what I'm going to show you how here. So we will do an input. It will be a wire, and it will be a size n minus 1 down to 0. And we'll call that D. And then we will have an input and it will be a wire, and this will just be clock.
So this is 1, right?
Yeah, because the clock is always just going to be a 1-bit wire.
No comment after wire.
What's that?
No comment after wire.
No comment. Oh, yeah, no comment after wire. Thank you. Okay, and then we're going to have an output, and it's going to be a reg, and it's going to be the same size that data is, n minus 1 down to 0, q. Now we have to specify n, because as is, the compiler is going to tell us that this doesn't work. It says, I don't know what n is. You're high. So we're going to tell it what n is. We're going to say parameter n equals 1 tick b1. We will be able to change that to whatever we want when we create an instance of this module. So by default, we'll say that n is just a 1-bit value, but it can be any value that we want. All right. Let's say always at, and we want to trigger according to what we just read in our device. When do we want to trigger? What?
D is clock.
Yeah, on the pause edge of the clock. So, on the positive edge of the clock, we want to set, oh, this is tricky. No, a latch is not an edge triggered device. Yeah, it's just so long as it's high. So we can't use an edge in this case. In this case, we just want to trigger on D. And we want to say if clock is equal to 1 tick b1, q is equal to d, else is equal to q. That is one way of shortcutting the requirement. Make sense? All right. Yes, technically you can. It is, I recommend to avoid it unless you know that that's what you need. Most of the time when you've got this logic, you probably want a latch. However, we're creating a latch, so that's why we need this. It will still give me a warning, but it will work. It's the best I can tell you. It's one of those things where it's like, avoid it unless you know that you need it, and the only place I can really think of that you definitely need it is when you're defining a latch. There's your D latch. FSM, we have a clock divider, we have a D latch, and then finally we have our BCD to 7seg module. This guy can be downloaded from the assignment page, and all its job is to take a number from 0 to 16, a 4-bit number, and output it onto your 7-segment display. So BCD is going to be some number 0 to 16, and 7seg is going to be an 7-bit value, and you're going to have to put each one of those segments or bits onto the correct pin. And the pin assignments are right here. these are your pin assignments. Cool. And you actually don't need these inputs. These are here if you wanted to draw your 7-segment from like switches. In our case, we're going to be driving our 7-segment from another module based on a clock. So you don't need these inputs. But when you go to put it on the board, these are the outputs you'll want to use. Cool.
The pins.
What?
Like the pins.
Yeah, the pins. Those are the pins you'll want to use. Saves you from having to look up all the pins in the user manual. And so that can just be downloaded. It's nothing too special about that. So the last thing is that you'll need to create a Lab 4 module, a top-level Lab 4 module, that will put all of this stuff together and will handle the logic for every state. And that's the part that I don't demonstrate for you because that's the bulk of this lab. So all the stuff I've just demonstrated is like new stuff you haven't seen before. The last part, you'll just create a new Lab 4. So module Lab 4 begin. Nope, no begin. End module. Cool. And then in here, you need to specify the inputs and the outputs, and you'll want to. So I'll make a little skeleton for you. I'll say inputs and outputs, and then in here you're going to want to create instance of all the modules. You're going to want to trigger when state changes. Also trigger when clock ticks. And then you're going to want to check if t is greater than 9 and handle that appropriately. And then what else? Oh yeah, out or connect T to the 7-segment display, and probably some other things that I'm forgetting. But that's kind of a basic kind of skeleton there for you. The stuff you want to think of. I will give you this one piece of advice as well. Separate your combinational always blocks from your sequential always blocks, your clock triggered ones. So your combinational ones are the ones that wait for inputs to change. Your sequential always blocks are the ones that listen for positive edges, like a clock. You'll want to separate those. It's just going to make your life easier. Okay. Anything else? No, I think that's it. Are there questions? Things you don't understand, things you want me to review? All right. Like I said, this is probably the most difficult lab that you've had to date. I won't say that you'll have because the next lab's harder. But this is the most difficult lab you've had to date. That's why you get 3 weeks to work on it. And good luck.